Dear students, welcome to the next lecture in digital communication. In the previous lecture, we were discussing about the general concept of signals in communication system, in a digital communication system, and we saw the example of a binary digital communication system where the source was sending ones and zeros, and when we had a zero we were mapping it to a particular signal S1T, and when we had a 1 that was mapped to another signal S2T. So ones and zeros were mapped to different signals and they were sent through the channel, and then in the presence of noise the idea is to detect those signals, and therefore the corresponding symbols or the corresponding bits in case of binary where that was sent. And while we try to detect or try to find an estimate of what was sent based on our observation of the received signals, we would always want to minimize the probability of error. And in the last video lecture we also saw that how same signal can be presented in different ways. For example, the magnitude and phase form, or the IQ or the quadrature representation, and how they were similar. And uh, and and we also mentioned in the last class that whenever we have a time domain signal that is received in the presence of noise, it is easier to analyze the signal if we can represent the time domain signal as just a number or just a dot in a signal space. It would be easier to find out an expression for the probability of error, and and therefore try to minimize that probability of error. So it's mathematically more convenient if we have a means to represent our time domain signals into a dot in the signal space. So we will go through the actual details of signal space concepts in this lecture. So to start with, first we have to understand the concept of vector space, because essentially a signal space is a vector space where the signals are represented as vectors. So don't get confused with this interchanging of the terms, because you will eventually see that on a high level they are identical. Okay, like if you represent, let's say, um, sorry, if you represent a signal or any quantity in a Euclidean space, like let's say x, y, and z, you have a 3D Euclidean space. So if you represent a point denoted by its coordinates x1, y1, and z1, then this is a point in the Euclidean space. If you draw a line from the origin, and then uh, this is 0, so then this is also a vector which has dimensions x1, y1, z1 in x, y, and z directions respectively, and the final resultant direction of this vector is denoted by this arrow. So So a point in a coordinate space or in an Euclidean space can also be conceptualized as a vector with a particular direction, uh, starting from the origin, and and different magnitudes along the different axis of the Euclidean space or the coordinate system. So basically, our ultimate aim is to represent a signal which is a time domain signal. Let's say it's ST, as a dot in the signal space, or equivalently a vector in the signal space. So therefore, let us first go through the concepts of vector space first. So in your linear algebra class, you probably have learned vector space. So we will just revisit those concepts here. So let's consider an n-dimensional space. So this is a three-dimensional space in this diagram. So let's extend that concept to an n-dimensional space with unity basis vectors e1, e2, up to en. So it's difficult to draw an n-dimensional space, but certainly I can draw a three-dimensional space. So let's say this is a three-dimensional space with three unity basis vectors. So let's say e1, e2, and e3. Okay, so these are the different unit vectors, and then we can define any vector in this space, let's say A, and that can have three dimensions, A1, A2, A3, and we can write A. So it's better to represent a vector by this notation. An arrow at the top suggests that it has a direction and it's a vector. So we can write this vector A as A1 times E1 plus A2 times E2 plus A3 times E3. So basically, this vector A has three different components, A1, A2, and A3, along the three axes or the three directions or the three unit basis vectors E1, E2, and E3. So the E1 component or the component of this vector across the E1 axis is A1, across the E2 axis is A2, and across the E3 axis is A3. So you can generalize this concept for an n-dimensional space. So you can write A as a summation like this from 1 to n, with AI representing the different components of this vector across the different basis vectors. So n is the dimension of this vector space, and basically it means that this is the minimum number of vectors that is necessary and sufficient for representing any vector A in this space. So with that, we can define different operations on this vector space. So we can have the inner product. So the inner product is between two vectors A and B is written like this, and this is basically A dot B, or the dot product, which is defined as this. So a sum over all the multiplications of the different components of A and B across the different unit vector directions. So let's say your A vector is A1, E1, A2, E2 plus A3, E3. So let's assume a three-dimensional space, and we have another vector which has components B1, B2, and and b3, sorry. So if you take the dot product of these two vectors, so basically you will have a1 b1 plus a2 b2 plus a3 b3, and this expression is basically obtained because of certain properties of the basis vectors. So basically if you do a dot b and then try to multiply each of these different components, the first term will be a1 b1 times e1 squared. So these unit vectors have unit energy. So basically if you write like this is basically the norm of the vector e1, okay, so which is 1 in this case. So basically if you take the square of these vectors or take the dot product of this unit vector with itself, it will be equal to 1, and and basically if you take the product of any of the cross vectors, for example e1 dot e2, it will give you 0, e1 dot e3 will give you 0. So based on these properties, that the norm of these vectors, of these basis vectors, are 1, and the cross dot products, or that's not the right way of saying, basically if you take the dot products of one unit vector, unit basis vector with another, then it will be 0. So this property renders the dot product a dot b as this expression a1 b1 plus a2 b2 plus a3 b3, because if you take these two terms, for example a1 b1 times e1 square will give you a1 b1. These two terms together, the product will be a1 b2 times e1 dot e2, so that will be 0. So all the cross terms will be 0, and then you will have a1 b1 plus a2 b2 plus a3 b3. So this is basically a revision of the prior concepts that you have learned in linear algebra. So so you see that these unit vectors, basically the dot product of them are 0, okay, so that means they are orthogonal to each other. In general, any vector, any two vectors, if their dot product is 0, they are orthogonal to each other, or in other words, they are parallel to each other. So if the dot product, sorry, not parallel, perpendicular, I'm very sorry. So they are perpendicular to each other. So in case of the unit vectors, they are indeed perpendicular to each other because they form the axis of the vector space, okay, or the Euclidean space. So basically they are all mutually perpendicular to each other, and therefore if you take dot products between e1 and e2, it will be 0. Between e1 and e3 it will be 0. Between e2 and e3 also it will be 0. So they are all perpendicular to each other, so that's why these properties are holding. So these unit vectors are orthogonal to each other, and they are also orthonormal to each other because they have unit energy, and that's what is said here. So a set of vectors are orthonormal if they are mutually orthogonal and all have unity norm. So the norm is defined by this term. So basically this is the square root of the total energy, okay, of the vectors. So basically it's the dot product of a vector with itself, okay, and if you do the dot product of a vector with itself, you will get the square of all the components summed together, and that also follows from these relationships. E1 dot E2 is 0, E1 dot E3 is 0, and the norm of these E1, E2, E3 are 1. So from there, if you write A in terms of A1, E1 plus A2, E2 plus A3, 3, and then if you take the dot of A with itself, you will end up getting A1 square plus A2 square plus A3 square. So generally speaking, this is the expression for the norm. So, so a set of vectors are orthonormal if they are mutually orthogonal. So let's say A and B are orthogonal if A dot B is 0, and if the norm of A is 1 and the norm of B is also 1, then A and B are also orthonormal. Okay, so they are orthogonal if the dot product is 0, and they are orthonormal if, in addition to the dot product being 0, they also have unity norm. And actually the unit vectors U1, E2, etc., they are all orthonormal because they have unit energy and their dot products are 0. So these unit vectors E1, E2, etc., of a vector space, they are called the basis vectors, and the property of them should follow certain rules. So first of all, they should be complete and they should span the entire vector space. So that means any vector A can be expressed as a linear combination of these vectors. And as I said in the previous slide, these basis vectors should be orthogonal to all others, and they also should be normalized. So that means for any I and j, the dot product of ei and ej, if they are not equal, I and j should be 0, and the norm will be 1. So so a set of basis vectors satisfying all these properties, all these three properties, they are called a complete orthonormal basis. Okay, so so having said that, what we discussed so far can be formally defined and summarized like this. So you can define a vector space basically that consists of a set V where the elements of V are called vectors. It also consists of a field F where the elements of F are called scalars, and the two operations, so an operation called vector addition that takes two vectors V and W in capital V and produces a third vector written as V plus W, which is also a member of the set capital V. And an operation called scalar multiplication should also be defined in this vector space that takes a scalar C that belongs to the field F and a vector V that belongs to the set of vectors V and produces a new vector written as CV, which is also in the set capital V. So basically a vector space is not only a set of vectors, but it also consists of a set of scalars, because whenever you are multiplying a scalar with a vector, the resultant is a vector. Okay, and whenever you are adding two vectors together, the resultant is also a vector. So all this scalar multiplication with a vector and addition of two vectors, all these things has to be defined, and they should be a part of a universal system that is called vector space. If your vector space definition doesn't contain all these together, then you probably cannot write a vector as this. Okay, because let's say these a1, a2, a3, these are actually scalars. Okay, and you are multiplying the scalars with these unit vectors, and then you are adding them together to get a vector a. So this addition and this multiplication also needs to be defined along with the definition of the vector space. Okay, so every operation that you are doing within the vector space has to be defined and should be the part of the entire system, and together formally they are called vector space. So that is why a vector space consists of a set V of vectors and also a set F of scalars, where the set F is called a field, and the operations for addition and scalar multiplication. So so this is the whole concept of a vector space, and the vector space also follows these axioms. So these are also important. So associativity of a vector addition. So you have two vectors u plus v added together, and then you add w. You can also write this as v plus w added first, and then u plus v plus w for all u, v, w in v. There should be an existence of a zero vector. So a vector in v written 0 and called a zero vector, which has the property that added with any other vector u, it gives the same vector back. Then the existence of negatives, this is also important. So there should be a vector minus u, which is also a member of the capital V set and called negative of u, and which has the property that if it is added with u, then it gives you the zero vector. Then you should have the associativity of multiplication. So any two scalar a and b in F, and for a vector u in V, this property should hold. And then we should also have distributivity, and we should also have unitarity. So these are the properties of a vector space, or rather axioms of a vector space, and the formal definition of the vector space. So now, borrowing these concepts, we will be defining a signal space. So basically, a signal space is nothing but a vector space where the signals are represented as a vector. Okay. So again, don't get confused, because when we started this discussion, I was saying that we will be representing a signal as a dot in this signal space. So your signal S1 can be represented a dot, but this is also equivalent to a vector starting from the unity, starting from the origin. And if you have different directions, then you can have a signal that is represented by its components along the different unit vectors. Okay, so the geometric representation or the coordinate space representation or the Euclidean space representation, all are identical and they mean the same thing. So we can look into a signal as a dot in the signal space. We can also look into that signal as a vector in the vector space of the signals. So signal space is basically a vector space, a special kind of a vector space where a signal can be represented by n-dimensional vector. Okay, so a signal S can be represented as an n-dimensional vector. So how to do that? Okay, so if we can find n signals named as phi1t, phi2t, phi n t, and we can write a signal, any signal, xt, or let's say st again, what's in a name. You can name a signal as st or xt, whatever. If you can write xt as a linear combination of these n signals, phi1 t, phi2 t up to phi n t, then with individual components xi, so let's say x1 times phi1 t plus x2 times phi2 t, and so on. So xn times phi n t. So, and so you can see, if you can find such signals, phi1 t, phi2 t, phi n t, if you can find n such signals, you can write xt, any arbitrary, any signal, xt, yt, st, whatever. You can write, if you can write it in this form, and also if you can ensure that these phi1 t, phi2 t, etc., they are orthonormal to each other, then you can say that your xt is basically a vector with the magnitudes x1, x2, dot 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 up to xn. So you see where I'm going. Basically, let's simplify this concept to the case of two-dimensional. Let's say I have a two-dimensional space, okay, or maybe a three-dimensional space, okay, and if I can find three signals, phi1 t, phi2 t, and phi3 t, let's say, and if these three signals hold the property that the energy of these signals, let's say phi1 square t dt integrated between 0 to tb, let's say, is 1, okay. Similarly, phi2, this is also 1, let's say. Similarly, phi 3, let's say this is also 1, and then all the individual correlations or individual dot products, let's say, are 0, okay. Let's say phi 1 t times phi 2 t, if you integrate this over dt, this is 0. Similarly for phi 2, phi 3, if you get 0, and for phi 3, phi 1, if we get 0. So if you can make sure that you find three signals, phi 1, phi 2, phi 3, and if you can ensure that the energy of them is equal to 1, phi 1 square dt integrated over all values of phi 1 is 1. Similarly for phi 2, this is 1, for phi 3, this is 1, and if you also ensure that the phi 1, phi 2 products integrated are 0, then you can say that phi 1, phi 2, phi 3 are orthonormal to each other, and then you can imagine that as if phi 1, phi 2, and phi 3 are behaving like a vector space, okay, a three-dimensional vector space whose three unit vectors are defined by phi 1, phi 2, and phi 3. And then if you can write your signal xt as x1 times phi 1 t plus x2 times phi 2 t plus x3 times phi 3 t, then in this coordinate space, or in this vector space, which is defined by phi1, phi2 and phi3, you can write your x as this one, which has three components, x1, x2 and x3. So you can transform this time domain signal xt into a vector x with components x1, x2, x3 if you can represent xt as x1 times phi1t, x2 times phi, plus x2 times phi2t plus x3 times phi3t. And this phi1, phi2, phi3, these functions follow these rules that their norm or their energy is equal to 1, and if we take the dot product of phi1, phi2 or phi2, phi3 or phi3, phi1, they are all 0. So in that case we can think that this time domain signals phi1, phi2, phi3 are three unit vectors that spans a three-dimensional vector space where the signal xt, which is a linear combination of phi1, phi2, phi3, can be represented as a vector with components x1, x2, x3. So this is the whole concept of a signal space. So as I was saying, so if you can think of this phi1, phi2, phi3 up to phi n as orthogonal to each other. So orthogonality means this. So for any j and k, if you take the product and integrate them, it will give you 0 for j not equal to k, and it will give you some constant cj for j equal to k. And if you can also make sure that this cj is 1, then this is called a orthonormal set. And then you can represent your signal using this orthonormal set like this, and each component of the signal x1, x2 up to xn can be given by this expression. Okay, so so this is how you can represent any signal in time domain into a vector in a vector space that is defined by this orthonormal set phi k t. Okay, so so yeah, this is the summary of what I discussed so far. And now let's focus ourselves on the binary digital communication scenario where we had two signals s1t and s2t. So let's consider any two arbitrary signals s1t and s2t. You saw in case of binary amplitude shift keying, s1t is 0 and s2t is v sine 2 pi fct. In case of your binary phase shift keying, you saw that s1t is the sine function and s2t is the 180-degree phase shifted version. So s1t and s2t can be any two arbitrary signals, and if you can find out two orthonormal basis functions phi1t and phi2t, where phi1t and phi2t are orthonormal, if this condition holds, so integration of phi1t phi2t over all the values of t gives you 0, and the energy or the norm of the phi1 and phi2 is equal to 1. So then you can represent s1t as s11 times phi1t and s12 times phi2t, where s11 is the component of the signal s1 along the phi1 direction, and s12 is the component of this signal along phi2 direction. And similarly you can represent s2 as s21 times phi1t and s22 times phi2t, and then you can obtain this s11, s12, s21, s22 as this. So this is the general expression for these components. So Sij is basically the projection of Si across phi j. So mathematically this is Si times phi j integrated over all values of t, and you can get Sij, where I can be 1 and 2 and j can be 1 and 2. So basically this can be represented as a vector space or a two-dimensional signal space where you have a phi1 axis and a phi2 axis. So notice that this phi1 and phi2 are still functions of time, and the original signals are also functions of time. So you are just representing them as some scalar multiplied by phi1t plus some scalar multiplied by phi2t. So this is a time function, this is a time function, this is a scalar, this is a scalar. So the entire expression is still a time function, but we are visualizing this phi1t and phi2t as if they are two unit vectors as represented by these two direction, phi1 and phi2, and then you can represent s1t, which is a time domain signal, as a vector starting from origin of the signal space and having this direction. Okay, and the projection of s1 on the phi1 axis is s11, so that is what s11 times phi1t, and the projection of s1 on phi2 is s12, and that therefore s12 times phi2t. If you visualize this as just a dot in this signal space, then also this s1t as if it's a point in this signal space with two coordinates, s11 and s21. Okay, so let's say this is your x-axis and this is your y-axis. You can also see it in that way, and s11 is your x coordinate and s21 is your y coordinate. So s11 is your x coordinate and s12 is the y coordinate. Similarly, you can represent s2, the other signal, in the same signal space or the same coordinate space or the same vector space, whichever you want to call it, and then it will have a component s21 along the phi1 axis or along the x-axis, let's say, and s22 is the other component along the phi2 axis or let's say the y-axis. So now we can see that we now have a trick in our hand that we can represent any time domain signal as a linear combination of two orthonormal functions, phi1t and phi2t. In fact, we can extend this to phi1t, phi2t up to phi nt. So any signal can be represented as a linear combination of two or more unit vectors or two or more time functions which are behaving like a unit vector by virtue of their property that they have unit energy, and if integrated with multiplying between phi I and phi j, where I not equal to j, we will get a 0. Then we can define the signals s1t, s2t, or any signal, any time domain signal, as a linear combination of this phi 1, phi 2, and so on, and we can form a vector if we conceptualize, or if we visualize a vector space or a signal space that are spanned by this phi 1, phi 2, phi 3, and all these orthonormal basis functions. So now the question is how to choose these orthonormal functions so that we can have S1 and S2 t exactly represented in terms of phi 1 and phi 2 t, and then we can draw a set of axes like this, phi 1 t and phi 2 t, and then represent the signals as dots or vectors in that coordinate system. So what is the algorithm? How do we find phi 1 t and phi 2 t? So we will see that in the next video lecture. I will stop here for now. Thank you.